This is lecture 3 of the Quantum Formalism Differential Equation Review lectures, and this time we'll be covering second-order linear homogeneous equations and the Wronskian determinant. Okay, so to get started, we could do some nonlinear first-order equations if they were separable, but in the second-order case, we won't have any techniques like this, so for the most part, nonlinear equations will be pretty hopeless. And so we will start out with second-order linear equations. We saw this standard form in the second lecture when we were talking about the existence and uniqueness theorem there. So here we have three coefficients that can be functions of t, which are p of t, q of t, and g of t. And here we have some terminology that a linear equation like this will be called homogeneous if this right-hand side is equal to 0, and non-homogeneous otherwise. So we'll be starting with the homogeneous case. We'll get to non-homogeneous equations later. The basic idea is you need to know how to solve the homogeneous version first, and then you can use some techniques to solve the non-homogeneous case after that. Okay, but even linear ones in general are too hard, so the one case we will really be able to do is the constant coefficient case. So you have a linear second-order equation, and you have constant coefficients. So that'll look like this. A, B, and C are real constants. They could be complex as well, but in certain classical mechanics, you're usually interested in functions of real variables. In quantum mechanics, you may well be interested in functions that have complex variables instead. Okay, so you can also put this in a standard form by dividing the whole equation by a, but sometimes there will be some polynomial equations that pop up, and sometimes they're easier to factor if you leave them this way rather than dividing by the a. It doesn't really matter too much. Okay, so here's our first example, y double prime minus y equals 0. Another way you can write this is y double prime is equal to y. And so what could some solutions to that be? Well, one that might jump out to you immediately is e to the t, right? That function is its own derivative, so it's its own second derivative as well. So that'll do it. And if you think a little bit harder, you can guess that e to the minus t is going to work as well, right? Because if you start with y is equal to e to the minus t, if you do one derivative, you'll get minus e to the minus t, which is not the same function. But if you do a second derivative, you get two minus signs which cancel out, and so you're back where you started. All right, so those are two solutions. And in fact, y equals c1 e to the t plus c2 e to the minus t is the general solution to this second order linear equation. Yeah, we'll see why that's the case later. But for now, more or less, all we know is that e to the t and e to the minus t are solutions. And I claim that this expression with two arbitrary constants is the general solution, right? Something having two arbitrary constants makes sense as the general solution because we know from the existence and uniqueness theorem that the initial value problems we're trying to solve have two initial conditions, right? The initial position and the initial velocity, like the initial value of y and the initial value of y prime. All right, so for the general case of constant coefficient linear homogeneous second order equations, will you be able to guess something similar, some kind of exponential function like e to the t or e to the minus t? And it turns out that the answer is yes. So which exponentials will work? Well, if you're not sure, you can just try y is equal to e to the rt, where r is some kind of constant. And then you want to figure out which values of r will work. And so to do that, you'll plug in y is equal to e to the rt, right? So we know that y prime will be r e to the rt, and y double prime will be r squared e to the rt. And now we just plug those into that equation. And so from this term, we'll get ar squared e to the rt. This will be b times r e to the rt. And this is c e to the rt. So all three of these terms end up having an e to the rt. And that's why you might think something like this will work, right? Because you just have these constants here rather than functions. And we know that when you have an exponential function like this, taking its derivatives, you'll end up with just some constant multiple of e to the rt. So all three terms will just be some constant times e to the rt. So we can factor out this e to the rt from the whole thing. And e to the rt is never 0, so it's okay to just cancel this e to the rt from this equation. That will be equivalent, right? This equation will only be equal to 0 when this equation is equal to 0. And we'll call this quadratic equation the characteristic equation associated to this differential equation, because e to the rt will be a solution if and only if it is a root of this quadratic equation. All right. So here's a statement that's quite nice. If R1 and R2 are real distinct roots of this characteristic equation, so if you don't have complex roots and you don't have a repeated root, you'll be in this situation where R1 and R2 are real distinct roots. And then I claim that this expression y is equal to c1 e to the r1t plus c2 e to the r2t is the general solution to this differential equation, second order linear homogeneous equation with constant coefficients. So at least in this case where the roots are real and distinct, we'll know the general solution. And again, I'll get to why this actually gives you all the solutions. That's what we'll be getting to later on in this lecture. Okay, so before that, let's just take that on faith and do an example. So let's try to solve this initial value problem, y double prime plus 3y prime minus 4y equals 0. And again, since it's second order, we need these two initial conditions, y of 0 equals 2 and y prime of 0 equals 17. All right, so the characteristic equation in this case is just r squared plus 3r minus 4 equals 0. And yeah, I picked a nice one that just factors really nicely. We don't have to worry about using the quadratic formula or anything, right? This will just be r plus 4 times r minus 1. All right, that's not too bad. So the roots are just r1 is equal to negative 4, r2 is equal to 1. And so if you believe the thing I said about the general solution in the case of real distinct roots, this will be the general solution to this differential equation. And now we just have to find the values of these constants, c1 and c2, that solve this initial value problem. We know from the existence and uniqueness theorem that it'll have a unique solution. And so there should be, if this is the general solution, there should be some values of c1 and c2 that'll actually work. All right, so how do we find those? Let's take the derivative of this general solution, and then we need to plug in the initial conditions to these two equations. All right, so if we take the derivative here, we'll get minus 4c1 e to the minus 4t is the derivative of this first term, and then the second term is left unchanged. It's just c2 e to the t. And now we plug in our initial conditions, right? So we're plugging in to this first equation, we're plugging in t equals 0, y is equal to 2. And this second equation, we're plugging in t is equal to 0, y prime is equal to 17. And so these exponentials will just go away, right? E to the 0 is just equal to 1. We'll have a 2 on the left-hand side of the first equation and a 17 on the left-hand side of the second equation. All right, so now this right here, 2 is equal to c1 plus c2, 17 is equal to minus 4c1 plus c2. This is just a system of two linear equations with two unknowns, which are these constants c1 and c2. And so to solve this, we'll need to do some linear algebra. Okay, so if we just subtract the two equations, right, that will cancel out the c2s. We'll get a minus 15 on the left-hand side, and then a positive 5c1 on the right-hand side. All right, so that tells us that c1 is equal to negative 3. And then if we plug that back into the first equation, we get 2 is equal to minus 3 plus c2. and that tells us that C2 is equal to 5. Okay, so we have y is equal to minus 3 e to the minus 4t plus 5 e to the t as the solution to this initial value problem. Okay, so we could find constants that actually worked. It involved a little bit of linear algebra, but it wasn't too bad. All right, so now let's get to this claim of why doing this linear combination with these arbitrary constants C1 and C2 will actually give you the general solution when in this real distinct root case. All right, so it actually comes from some principles that apply to more general linear homogeneous differential equations, not just the constant coefficient case. So this first theorem will tell us if we have two solutions, then we can actually, then taking linear combinations will give us more solutions. So this isn't saying that we have all the solutions yet. It's just saying that if you start with two solutions, you can do any linear combinations you want and you'll still have a solution. So adding them together, multiplying them by a constant, you'll still have a solution. And this is very important that we're still in the homogeneous case. This 0 over here is quite important for this principle of superposition. Okay, the proof is really not hard at all. Essentially, it's just that because we have this linear differential equation, we can view the left-hand side as just sort of a linear operator on y. So it will play nice with sums and constant multiples. That's the basic idea. But if you want, you can just plug things into the differential equation, right? If we take the first derivative, derivatives play nice with constant multiples and additions, so y prime will just be c1 y1 prime plus c2 y2 prime, and similarly y double prime will be c1 y1 double prime plus c2 y double prime. We can plug that into the differential equation, and now we can just collect all the terms involving y1 and collect all the terms involving y2. All the terms involving y1 will have a factor of c1, right? There's a c1 appearing with the y1 double prime in the second derivative, there's a c1 appearing with the y1 prime in the first derivative, and there's a c1 appearing with the y1 in the original function. So we can factor out a c1 from everything. And then what we're left with is just the original differential equation with y1 in place of y. And similarly, if we collect all the terms involving y2, we can factor out a c2, and what's left is just the original differential equation with y2 in the place of y. All right, so this will go to 0, and this will also go to 0 because we have the hypothesis that y1 and y2 are solutions. All right, so yeah, then we end up with 0 plus 0, so we're good. Anything like this will be a solution. All right, so that's the principle of superposition. We can do linear combinations of solutions as long as we're in this homogeneous case, and we will get a solution when we do that. Okay, this is just a reminder of the second-order linear existence and uniqueness theorem from lecture 2, which says that as long as P of t, Q of t, and G of t are continuous on some open interval containing your initial t value, then every initial value problem at t0 will have a unique solution that will be defined on this full interval from alpha to beta. All right, in other words, in order to, if we want to show that linear combination like this, y is equal to c1 y1 plus c2 y2, where c1 and c2 are arbitrary constants, we want to show that that's the general solution. All we need to show is that we can solve every initial value problem. And that's from the uniqueness part of this theorem. Because there's a unique solution to every initial value problem. Any solution defined at t0 has to solve some initial value problem. Namely, you just take the value of that solution at t0, and that will be y0, and take the value of the derivative of that solution at t0, that's y0 prime. So any solution has to solve an initial value problem, but every initial value problem has a unique solution. So if our supposed general solution can solve every initial value problem, then by uniqueness we know that we found all the solutions. Okay, right, so this is what I was saying. In order for this to be the general solution, we need to show that we can solve all the initial value problems with an appropriate choice of C1 and C2. All right, and so let's see what that looks like. Again, when we take this derivative, we'll just get C1 y1 prime plus C2 y2 prime. And so now we can write this initial condition at t0 using the following two equations, right? This equation is y of t0 is y0, and this equation is y prime of t0 is y prime 0. Okay. And if you look at this, this is a system of two linear equations if you treat C1 and C2 as the variables. And so you can write this in the following matrix form. This matrix y1 of t0, y2 of t0, y1 prime of t0, y2 prime of t0 times the column vector c1, c2 is equal to the column vector y0 and y0 prime. We want to show that for any values of y0, y0 prime, we can find a solution for these constants c1 and c2. And so linear algebra tells us that we can do that if and only if the determinant of this matrix is equal to is non-zero. So we want the determinant of this thing to be non-zero. Yeah. So linear algebra tells us this as a unique solution for C1 and C2 if and only if the determinant of this matrix is non-zero. And so that will lead us to the following definition. This determinant of that matrix is called the Wronskian determinant of the solutions y1, y2 at the point t0. So we'll use this notation W of y1, y2 at the point t0. Yeah, and this is just writing out that determinant algebraically, right? We have y1 of t0 times y0 prime minus y2 of t0 times y1 prime. That's the determinant there. Okay, so as an example, we can look at the solutions e to the t and e to the minus t from the first example in this lecture. So to do that, we leave the first function alone, so that'll just be e to the t0. We take the derivative of the second function. That's minus e to the minus t0. Then we leave the second function alone here. That's e to the minus t0. And we take the first derivative of the first function here. But the first function's e to the t, so that's its own derivative. So we just get e to the t0. And this will just end up being negative 2, right? This is minus 1. And this is 1. So we have minus 1, which is equal to negative 2. All right, so that will be non-zero for all values of t0. Or in other words, in terms of the linear algebra, we know that every initial value problem will have a solution of this form. We can choose appropriate constants C1 and C2 so that it works. All right, so that tells us that indeed this expression will be the general solution in this case, for the first example, where we know that e to the t and e to the minus t were solutions. Superposition tells us that something like c1 e to the t plus c2 e to the minus t, anything that looks like this will be a solution, and we can solve every initial value problem. No matter what the value of t0 is, the Wronskian's non-zero, so we can solve any initial value problem. We can find the appropriate values of C1 and C2 that work. And so that means this is, in fact, the general solution. Okay. I claimed that this actually worked for not just this first example, but any constant coefficient linear homogeneous second order equation where the characteristic equation has real distinct roots. So that's a slightly harder calculation, but still pretty easy. So if R1 and R2 are distinct real numbers, then the Wronskian determinant of e to the R1t and e to the R2t, well, that'll be the following. So here we leave the first function alone, take the derivative of the second function. So that'll be R2 e to the R2 t0 will be the derivative of the second one. Right, so this first term is y1 times y2 prime minus y1 prime times y2. All right, so yeah, here we take the derivative of the first function, so that'll be r1 e to the r1 t0. Leave the second one alone. All right, now if we look at these two terms, if we multiply the two exponentials, there's a rule of exponentials that say we just have to add the exponents. So both terms will end up looking like a constant times e to the quantity r1 plus r2 times t0. And the constants out in front will be r2 minus r1. And since we know that r1 and r2 are distinct, that tells us that r2 minus r1 is non-zero. This exponential can never be 0. So yes, this Wronskian is never 0 for any value of t0. All right, so now we've shown the claim from earlier that in the real distinct root case, we know that these are solutions by that characteristic equation calculation we did. And then superposition tells us that anything like this will be a solution. And now this Wronskian calculation tells us we can solve all initial value problems. So that tells us that we found the general solution in this real distinct root case. Okay. So I have one more theorem, which is quite nice, which says that we don't actually need to show that the Wronskian is non-zero at every value of t0 in an interval. We just have to find a single point where it's non-zero. So in these previous two examples, we did actually see that this Wronskian was never 0, but it would have been enough just to find a single value of t0 where the Wronskian doesn't vanish, according to the following theorem. All right, what does it say? It says that if you have a second-order linear homogeneous equation, these coefficient functions p of t and q of t are continuous on some interval, then in fact the Wronskian can be written as a constant times e to the minus integral of p of t dt. And this thing is never 0, right? It's an exponential function. Right, this constant c can depend on y1 and y2, but not t. So it's a constant in the sense that it doesn't depend on t. All right, yeah. And so because we have this expression for the Wronskian as a constant times an exponential function, that means that it's always 0 or never 0, right? It's either always 0 if this constant is 0, or it's never 0 if the constant is non-zero. Because if the constant's non-zero, it's a non-zero constant times this exponential function that's never 0, so it'll never be 0. Okay, so how do we get this formula for the Wronskian? The answer is that we do a little bit of algebra and then solve a first-order differential equation. So first, we know that y1 and y2 are solutions, so we can plug them into the differential equation and know that we'll get 0 on the right-hand side. And then the idea is that you multiply this first equation by negative y2 and multiply this entire second equation by positive y1, and then you add them together. And when you do that, these q of t terms will cancel, right? You'll have minus q of t y1, y2 from the first one and positive q of t y1, y2 in the second one. So those terms will cancel. Then you'll get minus y1 prime, y1 double prime times y2. That's this first term here. You'll get positive y1, y2 double prime. That's the second term there. And then you'll have two terms that will both have a factor of p of t. Those are coming from the middle terms in the previous equations. So you have minus y1 prime times y2 from here. And then you'll have positive y1, y2 double prime from here. All right. So we've gotten rid of the q of t terms, but it's not quite clear what we've done other than that, except if you notice that this term in parentheses right here is actually the Wronskian. Right? We have y1 times y2 prime minus y1 prime times y2. That's exactly the Wronskian of y1 and y2. And also, the other two terms that show up here are actually the derivative of the Wronskian. Right? If we take the derivative of the Wronskian, we have to use the product rule on both of these terms. So here we'll get y1, y2 double prime plus y1 prime, y2 prime. That's the derivative here. And then the derivative here we'll get minus y1 prime, y2 prime minus y1 double prime, y2, using the product rule there. And then these middle terms cancel. And so we're left with y1, y2 double prime minus y1 double prime, y2. And that's exactly what we have up here. Okay, so using that, we can rewrite this above equation as a differential equation, which is that the derivative of the Wronskian with respect to t plus p of t times the Wronskian is equal to 0. And this is exactly the kind of first-order separable equation we already know how to solve. Something almost exactly like this showed up when we were doing the method of integrating factors. And that has a solution which is a constant times e to the minus integral of p of t dt, right? So we'd first write it as dw dt is minus p of t times w, where here w is the Wronskian of y1 and y2. And then you just divide by w on both sides. And then you integrate both sides. And if you do that, you'll have natural log of w is minus the integral of p of t plus c. And now if you solve for w, you'll get exactly this. C times e to the minus p of t dt. Okay, so that's Abel's formula. And that tells us that the Wronskian is always 0 or never 0 if you're on an interval where both the coefficient functions are continuous. Okay, so now we'll just collect all our thoughts into this theorem. So this is just a summary of everything we've already done. So suppose that y1 and y2 are solutions to this second-order linear homogeneous equation defined on an open interval, alpha to beta, where p of t and q of t are both continuous. Then this family y is equal to c1 y1 plus c2 y2 with c1 and c2 arbitrary constants includes all solutions to this differential equation defined on this interval if and only if there's a single point in the interval where the Wronskian is non-zero. And so in that case, we have a family of solutions that includes all possible solutions to the differential equation, so it makes sense to call something like that the general solution to the differential equation. All right, so we have a single point where the Wronskian's non-zero. Abel's theorem tells us that that means the Wronskian's non-zero on the entire interval. Our linear algebra calculation tells us that that means we can solve all initial value problems. The existence and uniqueness theorem means that we have all solutions. And the superposition principle tells us that anything like this is actually a solution. So bringing all those facts together is what tells you that this must be the general solution. Okay, great. So I think I will stop there. Here's the quantum formalism links. And next time we will continue on with second order linear homogeneous differential equations with constant coefficients, and we'll look at those cases where we don't have real distinct roots. So the complex roots case and the repeated roots case.